Hi, my name is Michael Pendazis, and this is Math 241, Probability and Statistics. This is lesson number 10, and we're going to cover 6.10 and chapter 7 in this lesson. Okay? Okay. So, first, we're going to cover 6.10, which is on more applications. Okay? So 6.10.1 is entitled Estimating the Means of Distributions. And so here, if x is a random variable and x of I is the ith observed value of x, then the strong law of large numbers tells us that the sum from I equals 1 to n of x of I divided by n is approximately mu, which is the mean, with great probability, probably close to 1, if n is large. Okay? So if x is a random variable and x of I is the ith observed value of x, then the strong law of large numbers tells us that the sum of all the x of i's divided by n is approximately mu, with great probability if n is large. Okay? And so this is an application of the strong law of large numbers. And so if you perform an experiment and if you test the values of an experiment n times, and you record the values n times and you add them up and you divide it by n, then you're getting approximately the average value with great probability if n is large. Okay, and so the homework is going to be just one problem. And so the homework is on the homework sheet. Sorry for that. And so the homework is for this section 6.10. The homework is 6.10.2. The homework is page 223, exercise number 1. Okay? And so all you need to know is this to do that problem. Okay, so we're done with chapter 6 completely now with that. And so now the rest of the lesson will be on chapter 7. Okay, so chapter 7 is on what's called multivariate distributions. Okay, so chapter 7 is on multivariate distributions. And so 7.1 is an introduction, so let's start with 7.2, which is on, again, multivariate distributions. Okay, and so 7.2.1 is on multivariate probability functions. And so definition 7.1 is the multivariate probability function of the discrete random variable variables x1 to xn is the function f defined by f of x1, comma x2, comma dot dot dot, comma xn is equal to the probability that x1 is equal to little x1, x2 is equal to little x2, comma dot dot dot, xn is equal to little xn. For all possible values, for all values of x1 to xn of the variables capital X1 and capital Xn, respectively. Okay, so definition 7.1 is the definition of a multivariate probability function. Okay, so the multivariate probability function of discrete random variables x1 to xn is the function f defined by this equation. Okay, it's the probability that these random variables at capital X1 to capital xn take the values little x1 to little xn. Okay? And this equation has to hold for all possible values of x, little x1, little xn, of capital X1 and capital Xn, respectively. Okay? And I'll abbreviate multivariate probability functions by MPF. MPF will be the abbreviation for multivariate probability function. And if they add more words in between here, I might add another letter, but I'll tell you about that later. Okay, so right now, multivariate probability function will be abbreviated by MPF. By MPF, I'll mean those words. Okay? So let's keep going. Okay, so that's the definition of a multivariate probability function. So example 7.1. Okay, so the experiment here is to roll a die, roll one die, and to toss a coin. So you do those two things. You roll a die and toss a coin, and x1 is the value on the die, and x2 is the number of heads on the one coin toss. Okay? And the goal is going to be to find the joint probability function of x1 and x2. Okay? So the goal is to find the joint probability function of x1 and x2. It's the multivariate probability function of two variables. That's what a joint probability function is. It's the multivariate probability function for two variables, for two random variables. Okay? Okay, and so the solution, how we find that is, well, events x1 and x2, events capital X1 equals little x1 and capital X2 equals little x2 are independent events. Okay, so neither event affects the outcome of the other. Okay, so they're independent events. That implies that the joint probability function of x1 and x2, which is f of x1 comma x2, is equal to the probability that capital X1 equals little x1 and capital X2 equals little x2. And that is equal to the probability that capital X1 is equal to little x1 times the probability that capital X2 is equal to little x2, right? So saying this thing, that equal sign, is from the fact that they're independent events, right? The probability of the independent events means the probability of A intersection B is equal to the probability of A times the probability of B. And so here, the probability that both x1 equals little x1 and x2 equals little x2, that's the same as the product of each equaling probability this equaling that times the probability of that equals that. So that's what it means for them to be independent. And so then, what is the probability of any particular value in a die? It's 1/6. And what is the probability of getting a certain number of heads? It's 1/2. It's probability is 1/2 for getting 0 heads, and it's probably 1/2 of getting 1 head. Okay, so that's equal to 1/12, and that value of 1/12. So f of x1 comma x2 is equal to 1/12 for any value of x1 and x2, and so this is for x1 being from 1 to 6, and x2 from 0 to 1. And so you can choose any value of x1 from 1 to 6, and any value of x2 from 0 to 1, and then the probability that x1, that x2 is going to be 1/12. And so that is the joint probability function of x1, x2. That is the multivariate probability function for those two variables. Okay? And so that is example 7.1. Okay, example 7.3. Okay, so I'm going to let x equal to the number of outgoing local calls. And I'm going to let y equal the number of outgoing long distance calls. And so I could use quotes for calls again, but I'm just going to rewrite calls again. So x is the number of outgoing local calls, and y is the number of outgoing long distance calls during a 5-minute period. Okay? The joint probability function. So JPF is going to abbreviate for joint probability function of x and y. The joint probability function of x and y is the multivariate probability function of two variables, in this case x and y. Okay, the joint, using the word joint is just specific for when you have exactly two. Multivariate would be any number more than one. Okay, so multivariate probability function that we define is for more than one random variable, but if you specifically have more than one variable where it's exactly two, you could use the word joint. And so I'm using the terminology joint probability function of x and y here. So the joint probability function of x and y is given by this table. Okay, and so the table is this. Okay, so there's going to be three different values of y. There's going to be 0, 1, and 2. And there's going to be 5 values of x, 1, 2, 3, 4, 5, going from 0, 1, 2, 3, 4. And so that's going to be values of x, and those are going to be values of y. And so these are the probabilities for each one of those possible outcomes that I'm going to put into this 3 by 5 table. Okay, so what this table is saying, for instance, what is the probability that x equals 2 and y equals 1? It would be 0.05. What is the probability that x equals 4 and y equals 1 is 0.01. Okay, and then and it shows the other values, possible values too. And these are the values of the probability function f of x comma y. Okay, so the numbers in the box are the values of f of x comma y. The probability that x is equal to the number in the top here, and y is equal to one of the numbers over there. Okay, and so we're going to answer a few questions here. In part A, what is the probability of exactly two local and two long distance calls? I'll leave out the word calls. Okay, so what's the probability of exactly two local and two long distance calls? Well, that probability would be, there would have to be two local, x is the number of local calls, and y is the number of long distance calls, and so that would place us at exactly 0.01. And so for part A, the answer would be 0.01. Probability of exactly two local and two long distance calls. Right? Actually, I'll write a little bit more here in between. This is the probability that x is equal to 2 and y is equal to 2. That's f of 2 comma 2, and from that table it's 0.01. And so the answer to part A is 0.01. Okay, so the probability of, I'm going to do B now, so that makes sense. I'm going to erase this, and I'm going to go to B. Okay, so B, what is the probability of more than 3 outgoing calls? So it's not saying specifically 3 local or long distance, and so we're just more than 3 total calls where it could be local or long distance. And so this is going to equal f of 2 comma 2 plus f of 3 comma 1 plus f of 4 comma 0 plus f of 3 comma 2 plus f of 4 comma 1 plus f of 4 comma 2. Okay, so what I did here was I'm going to erase this red mark here with my hand from the last example, from A. What's happening now is you want more than 3 local calls, outgoing calls. And so the way we can have more than 3 total outgoing calls is if we have 4 local calls, or we have, right, if there's only 3 with 0, it wouldn't work. So now if we have 1, we'd need at least 3 here, and we could have 4 here. If there's 2, we'd need here. So these are all the probabilities, these are all the boxes in which the total number of outgoing calls is more than 3. 4, 0, 3, 1, 4, 1, 2, 2, 3, 2, and 4, 2. And so those 6 circles correspond with these probabilities. This one, this one, this one, this one, this one, and that one. Okay, so we have those 6 boxes correspond to those 6 values for the probability, and if you plug in these values, you get 0.01 plus 0.02 plus 0.01 plus 0.01 plus 0.01 plus 0.00, and if you add all those up, you get 0.06. So the final answer for part B is 0.06. Okay, so that's part B, the probability of more than 3 outgoing calls. Let's keep going. Erase these red circles for our next part. Pictures. Almost as good as it was. Part C. What is the probability of no outgoing, no local calls? Okay, so what is the probability of no local calls? Well, if there's no local calls, the local ones are the x values, right? So no local calls means the value of x is 0. So you have this one, or that one, the 3 I circled there. And so that would correspond with f of 0, 0 plus f of 0, 1 plus f of 0, 2. And so those values are 0.23 plus 0.11 plus 0.03. And if you add those up, it's 0.37. Okay, and so the probability of no local calls in total is 0.37. And so that's example 7.3. Okay, keep going. Okay, so now 7.2.2. That's multivariate, cumulative, multivariate, cumulative distribution functions. Okay, so my abbreviation for multivariate cumulative distribution functions will be MCDF. Okay, multivariate cumulative distribution functions. The M for multivariate, C for cumulative, D for distribution, F for functions. MCDF. Okay, so this is definition 7.2. Okay, so the MCDF, the multivariate cumulative distribution function of the random variables x1 to xn is a function capital F. Remember, FCN is my abbreviation for function. Is the function capital F defined by capital F of x1, comma, xn is equal to the probability that capital X1 is less or equal to little x1, capital X2 is less or equal to little x2, comma, capital Xn is less or equal to little xn. Okay, so that's the and this for all possible values of x1 to xn for negative infinity less than x of I less than infinity, and that's for all i's from 1 to n. Okay, so that's the multivariate cumulative distribution function. If 2 random variables are involved, because here in the definition we're talking about n, right? So n could be 10, 2, 5. So if 2 random variables are involved, n equals 2 in that definition, the multivariate cumulative distribution function, the MCDF, is the joint cumulative distribution function. And I'm going to abbreviate the joint cumulative distribution function by JCDF. So these abbreviations are all very similar, right? DF still means distribution function, C means cumulative, but J is now for joint. Okay? So you have a multivariate cumulative distribution function here. But if you're talking about 2, if n equals 2 in this definition, when you're talking about n equals 2, then we're going to call it specifically a joint cumulative distribution function, a JCDF. Okay, and so this multivariate cumulative distribution function, capital F, is the probability that these capital X's are upper bounded, are at most these little x values. So capital X1 is at most little x1, capital X2 is at most little x2, and so forth, up to including capital X of n is at most little x of n. Right? The little x's are just numbers or values. And so this is the probability that our random variables x1 to xn are at most those values. Okay? So let's keep going. That's the probability of the multivariate cumulative distribution function. Okay, so here's some important facts. Okay, so some important facts. So by definition, 7.3, which is the definition of a multivariate cumulative distribution function on the last board, if x and y are jointly continuous random variables. Okay, so if x and y are jointly continuous random variables with joint probability function, with j pdf, with joint probability density function f of x comma y, then we have these four facts. One, the j CDF, the joint cumulative distribution function of x and y, is capital F of x comma y, which equals the integral from negative infinity to y and the integral from negative infinity to x of f of s comma t ds dt for negative infinity less than x less than infinity and negative infinity less than y less than infinity. Okay? So we have a continuous random variable here, and so if you want to know what the probability that is that our variable capital X is at most little x and our capital Y is at most little y, you're going to integrate from negative infinity to x and negative infinity to y of your joint probability density function, little f there. Okay. 2. So here you would take right from the equation here. Okay. So you would look at this equation. Okay. You would apply that equation to a situation. For values a1 less than x less than b1 and a2 less than y less than b2, we have that the probability that a1 is less than x less than b1 and a2 is less than y less than b2. What that probability is the integral from a1 to b1, a2 to b2, and integral from a1 to b1 of f of x comma y dx dy, right? Because you're integrating f with respect to x from a1 to b1, and then afterwards you're integrating with respect to y from a2 to b2. Those are the range of values for x and y, and so you're integrating with those in mind, okay? And so here you would have this equation, okay? But that's for the conditions, right, for possible x values there. So those are the first two important facts with that given information. That's fact 1 and fact 2. Okay, fact 3. If capital C is the region of points x comma y in the plane, in the xy plane, and P of, in brackets, x comma y belongs to C, denotes the probability that the random variables x and y take on respective values little x1 and little x2 so that x comma y belongs to the sets capital C. So that x comma y, I'll say it another way, is a point in C. Then the probability that x comma y is in C, that the probability is equal to the double integral over C of f of x comma y dx dy. Okay? The integration is over region C, so this means, this is not my, I'm just pointing to that, means the integration is over the region C. And the probability is only defined, if the integral on the right exists. Okay, so only if this integral exists is that probability defined. And that integration over C, that's the integration over the region C. Okay? So the probability that x comma y is in C, where C is the region of points x comma y in the plane, is equal to the double integral over the region C of f of x comma y dx dy. And so here you would apply this equation, where that C is there still, it's integration over C. And that means that C means integration over the region C. Okay, so for instance, if you want to find the probability that if this was the region C here, right, that weird thing there was region C in the plane, then if you want to find the probability of a point x comma y being in that region C, you would double integrate over that region C of f of x comma y dx dy. Okay? And so that would be difficult to do with the region I showed. If it was a square, maybe it would be very easy. If it was a circle, you could change the polar coordinates and you could integrate that way, right? RD theta is dx dy, right? And so then, but you would find that integral over that region C. And that, if you could find it, that would be the probability that the point x comma y was in that region C. Okay, so that's 3. Okay, now 4. So if capital F of x comma y is a cumulative distribution function of x and y, then the joint probability density function, the JPDF function, is given by little f of x comma y is equal to d2 capital F of x comma y over d x dy. Okay, so if capital F is the CDF of x and y, then the JPDF function is given by that equation. At all values, at all x, y, where the partial derivative is defined. Okay, and the numbers x, y, and the numbers where x, y, so the values of x and y where the partial derivatives don't exist, you can assign arbitrary values for x. For f of x comma y. Okay, so little f is the d2 capital F dx dy at all points x, y where the partial derivative is defined. And for values of x, y where the partial derivative is not defined, then you can just assign any arbitrary value for f you want. Okay? So those are 4 important facts after that definition. Okay, and so here, before we get this equation, so that's the equation you would use there. Okay? Okay, so for a problem that uses these facts, you would want to look at that equation, and you would want to think how to apply the equations that I boxed to the problem that you're trying to solve. Okay? Example 7.7. Suppose xy, both of them are continuous random variables with a joint probability density function, that's JPDF, with joint probability density function, f of x comma y is equal to 1/2 x e to negative y for 0 less than x less than 2 and y greater than 0, and 0 elsewhere. Okay, so that region I'm talking about there, 0 less than x less than 2, y positive, that would be x out values from 0 to 2, and y would be positive. So I'm talking about this region here. It's above the x-axis, and it's from x between x equals 0 and x equals 2. Here, f of x comma y is that, and everywhere else it's 0. So here it's 0, here it's 0, here it's 0, there. Everywhere else, f is 0. But here it's that. Okay, so part A, we're going to find the joint cumulative distribution function of x and y. I'm abbreviating this JCDF, the joint cumulative distribution function, density function of x and y. Okay, right? And so that's our function capital F of x comma y, right? Which is equal to the probability that capital X is less or equal to little x and capital Y is less or equal to little y. That's the function we want to find here. Okay? And so for case 1, let me, I just wrote that down so you know what function I'm talking about. So for case 1, we want to consider for x less than or equal to 0 and any y value. Which I'm going to write any y value is y going from negative infinity to infinity, right? So capital F of x comma y in that case would be equal to the integral from negative infinity to y and the integral from negative infinity to x of f of x comma t ds dt. This is the probability, right? This is the probability that this is the probability that capital X is at most little x and capital Y is at most little y for a continuous random variable. Well, here we're looking at x less than or equal to 0, right? And any y value. When x is less than or equal to 0, the value of f is 0. And so this is just the integral from negative infinity to y and the integral from negative infinity to x of 0 ds dt, which is equal to 0. So capital F of x comma y is 0 for those x and y values. Okay, and that's because f here, this f is 0 because we're looking at values here to the left, right? When x is less than or equal to 0, any y value. And so we're going to get 0 here. And you integrate, double integrate 0, you get 0. Okay? Okay, so that's case 1. Case 1 is capital F is 0 there. Case 2. For any x value, for negative infinity less than x less than infinity, and y less than or equal to 0, then capital F of x comma y, right, is equal to, now we have a double integral here, and we're taking any x value, so x is going to range from negative infinity to infinity, and y is going to be less than or equal to 0, so it's going to go negative infinity to 0. And it's going to be little f of x comma y dx dy. So here's for x, that's for y. And then when x is any value but y is less or equal to 0, then for this situation we have y less or equal to 0 and x is any value. So there f is 0. And so if f is 0 there, then this is going to be the integral, double integral, of 0 dx dy, which is 0. And so now capital F there is also 0. And that's case 2. Okay? Okay, now case 3, for 0 less than x less than 2, when y positive, then capital F of x comma y is equal to double integral. Now x is going from 0 to 2, and y is going from negative infinity, from 0 to y, little y. And so why is that? Well, x is going from 0 to 2. Erase this here. X is going from 0 to 2, right? If x is going from 0 to 2, then those are the range of x values. Simple. If y is positive, well, the cumulative distribution, cumulatively we're going from negative infinity to that y. But the y, when y is negative, f is 0. And so the y values when y is negative don't matter. Only the y values when we start going above the x-axis, only positive values of y really matter, and we can include 0. So I'm going to go from 0 to little y. Okay, because now capital Y is at most little y, where y is positive. And so all that matters is when capital Y ranges from 0 to little y. Okay, so the region we're talking about here is from x from 0 to 2, and y is positive. And so if this is y, we're looking at this part, where we have some positive value of y, and we want to know the probability of that region there. And so that's f of x comma y dx dy. So s comma t, f of s comma t ds dt, right? S and t are dummy variables for the values of x and y, respectively. Okay, so now this is the integral. Oh, sorry, x is between 0 to 2, so actually I have to write this very similar thing here. This is going from 0 to x, because x now is from 0 to 2, and so x is not, fix this. Okay, so then here, this was the original whole region, but now we're only looking at it from this part of it. Looking at this part here, going from 0 to x and 0 to y, where y is positive and x is between 0 and 2. And so we're integrating from there to there, because everywhere else f is 0. Everywhere outside, right, when x is, these values x is 0 and these values of y is 0. So we only need to go from there to there. And then this is equal to, now, integral from 0 to y, integral from 0 to x of that function, which is 1/2 s e to the negative t ds dt. And I'm using s and t to mean x and y respectively because they're dummy variables. We're integrating with respect to dummy variables. So now here, this is equal to the integral from 0 to y, and here t is a dummy variable for y, and then I'm integrating from 0 to x times the integral from 0 to x of 1/2 s ds. S is the dummy variable for x. And then if you integrate both those things and multiply, you get 1/4 x squared, 1 minus e to negative y. Okay, so here, that's a capital F of x comma y in case 3 for those x values. We're only dealing, we have these, but then if we were to include the rest of it, let me just point this out, right? The rest of it would mean x is anything, y. Technically, all of that, where this continues in all directions and so does that. That would be the entire region. But then here it's 0, right? And so all of this doesn't matter. And so this part, again, this part doesn't matter. This green part. So the green part of the region we're considering, not that, the green part of the region is, f is 0 there. And so the only part where it's non-zero is that rectangle, which I'm integrating here. Okay? And so now that's case 3. So let's keep going. Okay. Okay, and then case 4. This is all for part A. Case 4 is for x greater than or equal to 2. For x greater than or equal to 2, y positive. Then if we want to know capital F of x comma y, well then that's going to equal the integral from negative infinity to y, integral from negative infinity to x of little f of s comma t ds dt. I'm just writing more steps here for case 4. And then if we look at this again, this is x and this is y. The x-axis and y-axis understood. Then if this is 0 and this is 2, then if x is greater than or equal to 2, for instance, if x is either 2 or greater than 2, y is positive, then the cumulative distribution function will consider this region. Continuing it out, so it's going to continue that way and it's going to continue this way, right? But we know that it's already 0. We know it's 0 here and here, right? And we know it's 0 here. Because if it's x is greater than 2, it's 0. So only this region do we care about the value. Only here could the value be non-zero, that when we integrate. And so we're only going to integrate over that region to find the value of that over the entire thing. And so that's going to be the integral from 0 to y, and then from 0 to 2. So now we're including up to 2 because x, we don't have to go up to x because x is further to the right, and so we only need to go up to 2. And so now we're going to integrate here. That's the red region, and the rest of the green region, this is 0 over here. And so if we integrate and find it here, we're finding it over the whole thing. And then that is 1/2 s e to negative t ds dt. And so then this is equal to the integral from 0 to y of e to negative t dt times the integral from 0 to 2 of 1/2 s ds. And so if you find both those definite integrals and then you multiply them, you get 1 minus e to negative y. And that's capital F of x comma y for those values of x. For x greater than or equal to y positive. And so with all 4 of those cases, you could then define capital F of x comma y as a piecewise function, where it's in 4 pieces, right? For each of the 4 cases. And then that's the answer to part A, finding the cumulative distribution, joint cumulative distribution function of x and y. Okay? Okay, so let me just erase this. And so our final answer, actually I'm going to write our final answer here, capital F of x comma y is going to equal 1/4 x squared 1 minus e to negative y, and that's for 0 less than x less than 2 y positive. It's 1 minus e to negative y for x greater than or equal to 2 y positive, and it's 0 everywhere else, 0 elsewhere. Okay, so I kind of condensed it here. That's capital F. That's the answer to part A. Okay, and so part B, we're going to find the probability that x is less than or equal to 1 and y is less than or equal to 2. Okay, and the probability that 1 is less than or equal to x, less than or equal to 2, and 3 is less than or equal to y, less than or equal to 4. So for the probability that x is less than or equal to 1, y is less than or equal to 2, so it's capital F of 1 comma 2. And so capital F of 1 comma 2 would just be if you plugged in x equals 1 here and y equals 2 there, and you would get 1/4 times 1 minus e to negative 2. Okay, they just plugged in x equals 1, y equals 2 because it falls in those range values. And then the probability of 1 less or equal to x less or equal to 2, 3 less or equal to y less or equal to 4, then what's that equal to is, well, it's a definite integral from 3 to 4, definite integral 1 to 2 of f of x comma y dx dy, because x is ranging from 1 to 2 and y is ranging from 3 to 4. And so this is the same limits of integration here of 1/2 x e to negative y dx dy. And that's because we're looking at x values between 0 and 2. When it goes from 1 to 2, it's between 0 and 2. And from when y is 3 to 4, it's y is positive. And so we're using this part of capital F for oh no, sorry, no, not there. We're using this. We're using that because actually, let me keep green here. We're using this here because little f of x comma y, right? These are the x values and y values, and so when x is from 1 to 2, it falls there. Those are positive y's, and so that's f for those range of values for x and y, respectively. And so that then when you integrate this, when you find the double integral, you get that that's 3/4 times e to negative 3 minus e to negative 4. And so now that is the probability that x is between 1 and 2 and y is between 3 and 4. Inclusive. Including it. Okay? So that's part B of example 7.7. And so we're done with that example. Let's keep going. So example 7.8. The x and y be continuous random variables with joint, which JPDF, joint probability density function, f of x comma y is equal to 2xy plus 3/2 y squared for 0 less than x less than 1, 0 less than y less than 1, and 0 elsewhere. Okay, and let capital C be the region in the plane such that a region of points x comma y in the plane such that x plus y is less than 1. And the goal is going to be to find the probability that the x comma y is in the region C. Okay, and so the solution is that the probability of x comma y belong to the region C is equal to the double integral over C of f of x comma y dx dy from earlier, right? That's how I defined that probability earlier, is that double integral. Well, then that's equal to the double integral over C, which is x is going to range from 0 to 1 minus y, and y is going to range from 0 to 1 of 2xy plus 3/2 y squared dx dy. And so let me explain that. So now here, if you have this region, you want to find, you're looking at the region where x plus y is less than 1. That's the same as saying y is less than 1 minus x, or y is less than negative x plus 1. And so if you look at the line y equals negative x plus 1, it's this line, where I just drawing this as a dotted line. But this would be y equals negative x plus 1. Okay? Negative x would be through the origin and slanted like that, and then plus 1 you would translate it up 1 unit. So that's y equals negative x plus 1. If you want y less than negative x plus 1, then it would just be all the points below that line, not including that line. So I'm gonna keep this as dotted. This line's gonna be dotted, and so this is the region C. That's the region C of points such that x plus y is less than 1. Region C is the set of all points x comma y such that x plus y is less than 1. That's the shape underneath that line. Those are all the points x comma y such that x plus y is less than 1. Okay, and so now if you want to integrate over that region C, first note that little f of x comma y is 0 everywhere other than where x is between 0 and 1 and y is between 0 and 1. And so where does this line cross the x-axis and y-axis? This point on y is 0 is the point 1 comma 0. And this point here is the point 0 comma 1. Okay? So those are the points here. 1 comma 0 and 0 comma 1. And so if f of x comma y is 0 everywhere other than for x and y values strictly between 0 and 1, then the only values we care about are in this triangle here. See where I shaded in green? That's the only part of region C where x is between 0 and 1 and y is between 0 and 1. Everywhere else, the x and y values don't satisfy those two inequalities, which means that f is 0 there. And so when you double integrate over f, you'd be double integrating over 0 everywhere other than over that green region. And so now we're just integrating over that green region. And if you're looking at that green region, where this is the point 0, 1, and that's the point 1 comma 0, and this is the part of the line y equals negative x plus 1, then how you integrate over that is just the double integral. If you draw a little rectangle here, then when you integrate with respect to x, you're going from 0 to oh, okay. Actually, so sorry. This rectangle is going to be sideways. So I'm going to integrate this way. And so when I integrate with this way, the rectangle going from the side here, like you wouldn't care. This is y equals negative x plus 1. I'm going to write this as x. This is equivalently the line x equals negative y plus 1. Okay, so now if x is going from all the way here to here, x is going from x equals 0 to x equals 1 minus y. I'm going to write this as, instead of negative y plus 1, I'm going to write x equals 1 minus y. That's the line here. So the x values are ranging from 0 to 1 minus y. And the y values then are ranging from 0 to 1, because the smallest y value is 0 and the largest y value is 1. And so it's going from 0 to 1. So the way you integrate over that triangle is the double integral from x values from 0 to 1 minus y and y values from 0 to 1. And that's the function here in this region. So in this region, f of x comma y is equal to that. And so you plug that in for f. And so when you double integrate that, the value you get, you double integrate that, and the value you get is 5 over 24. Okay? And so that's the answer to example 7.8. Okay, so now it's 7.2.4, which is on marginal distributions. Okay, so definition 7.4, part A. Let x and y be discrete random variables with JPDF, joint probability density function, f of x comma y. The marginal probability functions of x and y, respectively, are given by f sub x of x is equal to the sum over y of f of x comma y. So if x and y are discrete random variables with joint probability density function f of x comma y, then the marginal probability functions of x and y respectively are this. F sub x of x is equal to that. And what that means is that this is the this essentially is just, you're taking the values of f of x comma y, and you're just summing them up over all, for some fixed x, you're summing them up over all possible values of y. Now, so this little x is fixed. You're choosing a fixed value for capital X. And then you're asking yourself, well, what is the probability when you have two discrete random variables x and y, and you have a probability function that defines the probability where capital X is equal to little x and capital Y is equal to little y. When you're given that probability function that tells you the probability of two random variables, how do you know the probability that capital X is equal to just capital X is equal to the value little x? Well, it's just the sum of f of x comma y, where you sum up all the possible values of y while you keep x fixed. Okay? So here you just keep x fixed, and you take f of x comma y where x is fixed, and you change all the values, you consider all possible values of y here, and you add up f of x comma y where you change all the values of, you consider all possible values of y, you sum up over all the possible values of y. Okay? And note here, note that f sub x of x is equal to the probability that capital X equals little x, which is equal to little f of x. Okay? So this turns out to be the probability that capital X equals little x. And f sub y of y is equal to the sum over x of f of x comma y. And so if you fixed, this little y is fixed, and so f sub y of y is when you keep y fixed and you sum over all the possible values of x of f of x comma y. And note here that f sub y of y is equal to probability that capital Y is equal to little y, which is f sub y, f of y. So that's part A of definition 7.4. Okay? Part B. Let x, y be continuous random variables with joint probability density function JPDF f of x comma y. The probability that capital X equals little x and capital Y equals little y. The marginal probability density functions that's MPDFs of x and y, respectively, are given by f sub x of x is equal to the integral from negative infinity to infinity of f of x comma y to y, and f sub y of y is equal to the integral from negative infinity to infinity of f of x comma y dx. Okay, so the marginal probability density function of x and y respectively are, this is the marginal probability density function of x, and so you're just integrating over all possible values of y of f of x comma y where x is fixed. Again, here f is fixed. And here, the marginal probability density function of y is this function, where y is fixed, and then you integrate over all possible values of x with y being fixed of f of x comma y. Okay, so that's part B of this definition. And so that's definition 7.4. And so what we're defining here is the marginal probability density functions, MPDFs of x and y, where x and y are continuous random variables with joint probability density function f of x comma y. Okay, and so here you want these equations. This equation and this equation. Those are the two equations you use. Okay, so you want to study those two equations. Okay, next, note the probability that A is less than X less than B is equal to the probability that A is less than X less than B, and negative infinity is less than Y less than infinity, and Y could be anything. And then this is equal to the integral from negative infinity to infinity, integral from A to B of f of x comma y dx dy. So the x values are ranging from A to B, and the y values over from negative infinity to infinity. This is equal to the integral from A to B of the integral from negative infinity to infinity of f of x comma y dy dx. And so now I'm just switching the order of integration. Instead of first x then y, now I'm integrating with respect to y and then with respect to x. And so first you find that integral inside. That integral becomes the integrand of the outer function, of the outer integral. And so now this is equal to the integral from A to B. Well, what is that? That integrand is just f sub x of x. We define that integral to be f sub x of x, the marginal probability density function. The marginal probability function of x. That's what that integral is. And so we're integrate over that with respect to x. But we said that, I mentioned that this was f of x. Actually, okay, no, that's fine. So then that implies that this thing is equal to that. So what we get is the probability that A is less than x less than B is equal to the integral from A to B of little f sub x of x dx. That. Okay? That's the note there. Okay? Okay, let's keep going. Next, example 7.1. Example 7.14. Find the marginal, the MPDF, the marginal probability density function of random variable x of example 7.5. And find the probability that x is greater than 2. And so the solution, we can change. So the solution is that, no. So here's the joint probability density function of x and y, f of x comma y. And so I'm going to tell you that it's e to the negative x times e to the negative y for positive x and positive y. And it's 0 elsewhere. And so if you do this example, you would get that as the joint probability density function of x and y. That implies that f sub x of x is equal to the integral from negative infinity to infinity of f of x comma y dy. And that's by the definition of the marginal probability density function. And that's equal to the integral from 0 to infinity, because the negative y values don't matter, of e to the negative x, e to the negative y dy. Right? So f here, this f is equal to this, but only for a positive y. And so we don't need the negative y. And so we're only go from 0 to infinity for y values. And so when you find that integral, that improper integral, you get this is equal to e to the negative x. And this is, again, only for positive x, for x greater than 0. And so here, we said x is greater than 0, and so that's why x has to be positive there. Okay? And then it's 0 elsewhere. And so that's the marginal probability density function. That's the marginal probability function of x. Right, okay, that's it, okay. Now the probability that x is greater than 2, so we find the marginal probability density function of x, done. The probability that x is greater than 2 is the integral from 2 to infinity of f of x dx. Well, this is the integral from 2 to infinity of f sub x of x dx. And so I said those two things were equal. So I mentioned before that this thing is equal to that. Okay? And so now we're just integrating with respect to that. And so what this is e to the negative x. This is the integral from 2 to infinity of e to the negative x dx, which is equal to e to the negative 2. And that's equal to 0.1353. And so the probability that x is greater than 2 is equal to 0.1353. And so that's the probability that x is greater than 2. And so we know what that is. Okay, so now that's the answers to those two things for example 7.14. Okay. Okay, let's keep going. Okay, 7.2.5 is on conditional distributions. Okay, so x and y are discrete random variables. So x and y are discrete random variables, and so the probability that x is equal to x naught, given that y is equal to y naught, is equal to the probability that x is equal to x naught and y is equal to y naught, divided by the probability that y is equal to y naught. Okay, good. And so now this is equal to f of x naught comma y naught over f of y naught, f sub y of y naught. Okay, so the probability that x equals x naught and y equals y naught is f of x naught comma y naught, and the probability y is equal to y naught is equal to f sub y of y naught. And so what I'm saying here is that this is equal to that. Okay, and this is provided that the probability of y is equal to y naught is positive. So it can't be 0. You can't divide by 0 there. So we have to put the condition of the probability of the denominator, the probability y equals y naught is positive, not 0. Okay, and f sub x of x given y and y naught is equal to the probability that x equals x naught given y equals y naught. And that's equal to what I wrote there. F of x naught comma y naught divided by f sub y of y naught. Okay? And so what I'm saying is this is the notation for that thing I just found there. This is the notation for that, which I show is equal to that. Okay? So you can abbreviate this by writing that notation. Probably that x is equal to x naught given that y equals y naught and equals that. Okay? So that is the conditional probability function of x given y equals y naught. Okay, so that's a conditional probability function of x given y equals y naught. And so it's very much like conditional probability that we did earlier for a discrete random variable. Okay, and so continuing. F sub x of x given y is equal to f of x comma y over f sub y of y. And this is if f sub y of y is positive. And f sub y of y given x is equal to f of x comma y over f sub x of x. And this is if f sub x of x is positive. And so this is true for every x. This is true for every y. And both of these things, this and this, those are both true for both discrete and continuous random variables x and y. Okay, so you'll find the values of these f's here will be different, but this equation, these two equations, will be the same with those conditions for both discrete and continuous x and y. Okay. Okay. Good. Okay. Example 7.15. Let x, y be continuous random variables of example. So let x and y be continuous random variables of example 7.8. Okay, so then so let x, y be continuous random variables of the example 7.8. So the marginal probability function, of x is this by definition, and then that's equal to this, so this is for 0 less than x less than 1, and it's 0 elsewhere. Okay, that was so that was for the region of points, right? So C. Okay, and so and 0 elsewhere. Okay, and then f sub y of y is equal to integral from negative infinity to infinity of f of x comma y dx by definition of the marginal probability function of y. That's equal to, in this example, the definition from 0 to 1 of 2xy plus 3/2 y squared dx. And that's equal to y plus 3/2 y squared. And that's for 0 less than y less than 1. And it's 0 elsewhere. Okay, so these are the marginal probability functions of x and y respectively of example 7.8. Okay? So let me just remind you. In example 7.8, f of x comma y was 2xy plus 3/2 y squared, and that was for x strictly between 0 and 1 and y strictly between 0 and 1, and it was 0 elsewhere. So here, when I'm integrating here, the only x values that matter are only y values that matter from 0 to 1, and so I'm only integrating from 0 to 1 here. The other y values don't matter here, right? So here it's from 0 to 1 where it's not 0. And so when I'm integrating from negative infinity to infinity, I only need to consider from 0 to 1. And then the f here, this f of x comma y, that's this guy, and it's equal to that here. And so you're just integrating from 0 to 1 of f, and you're getting that. And then here, when you find the marginal probability function of y, x only matters from 0 to 1. And so we integrate from negative infinity to infinity with respect to x, you're going to integrate from 0 to 1. And then again, f here is this. And so this f is that function. You're integrating from 0 to 1, and you get that. Okay? So our conclusion is that capital F, so little f sub x is x plus 1/2 for those values of x, and f sub y of y is equal to y plus 3/2 y squared for y between 0 and 1. Between 0 and 1. Okay, and so that's part A. Okay, so let's keep going. So continue with the same example here. Continue with the same example here for part B of this. For 0 less than y less than 1, if we want to find f sub x of x given y, it's equal to f of x comma y over f sub y of y. And what that's equal to is, well, it's 2xy plus 3/2 y squared over y plus 3/2 y squared, which is equal to 2x plus 3/2 y over 1 plus 3/2 y. And this is for 0 less than x less than 1. And that's 0 elsewhere. So I'm going to have to rewrite the thing I wrote here so you can see what I'm doing here. F, I'm talking about in example 7.8, f of x comma y. Same f here. It's 2xy plus 3/2 y squared, such that 0 is less than x less than 1 and 0 less than y less than 1, and it's 0 elsewhere. And we found in the previous board that f sub x of x is equal to x plus 1/2, and that's such that 0 is less than x less than 1, and f sub y of y is equal to y plus 3/2 y squared, such that 0 is less than y less than 1. Okay? And so now this is our probability density function. These are our marginal probability functions. Okay? Okay, so with those three things, f sub x of x given y is f of x comma y over f sub y of y. And so what's f of x comma y? For y between 0 and 1, it's just this thing. And so it's this thing, which is f of x comma y, which is this, divided by f sub y of y. F sub y of y is this, which is that, for y between 0 and 1. And so you just plug that in there, and you just divide the two things, and you get that. And it's 0 everywhere else, because f is 0 everywhere else. And then if you do for 0 less than x less than 1, what you get is f sub y of y given x is equal to f of x comma y over f sub x of x by the definition of that, which is equal to 2xy plus 3/2 y squared. That's f of x comma y divided by f sub x of x, which is x plus 1/2. And that's for 0 less than y less than 1. And then, right, so then, and it's 0 elsewhere. That's because here, for that. Okay? So f here, this f is this. So f here is still this for x between 0 and 1 and y between 0 and 1. So that there and that there. So this is this and this is that. And then f sub x of x is x plus 1/2 for x between 0 and 1. Okay? And so now we see that here. Okay, and so this divided by that for those values. Okay, so now we found this is this, and we found this is that for those values of x and y respectively. So that's part B. Okay, now I'm going to erase this. Only the top part, so I have to rewrite the bottom stuff again. So I'm going to erase this. And then for part C, the probability that 0 is less or equal to x less or equal to 0.5 is equal to the integral from 0 to 0.5 of f sub x of x dx. And that's equal to the integral from 0 to 0.5 of f sub x of x, which is x plus 1/2, which is right there, dx. You calculate the differential, you get 0.375. Okay, and so, erase all these marks a bit here. Good. Okay, so now, okay, so x is ranging from 0 to 0.5, and so that's why the limits of integration are 0 to 0.5 there. F sub x of x is x plus 1/2 for x between 0 and 1, and that those x values fall between 0 and 1, so that's x plus 1/2 there. And then you find that differential, you get 0.375. And then if you find the probability that 0 is less than or equal to y, less than or equal to 0.4, you get the definition from 0 to 0.4 of f sub y of y dy. Right, that's the probability that when y is some fixed value, and if that fixed value is ranging from 0 to 0.4, that's that. And so now this is equal to the definition from 0 to 0.4. Well, what is f sub y of y? It's y plus 3/2 y squared for those values of y. And so for those values of y, it falls within that range. And so, right, so that range is these values here. And so f sub y of y is y plus 3/2 y squared. And that's dy. So I'm just plugging that in there, right? And so then that's equal to, that differential is equal to 0.3276. Sorry, no, that's equal to 0.112. Okay, that's part C. And then part D. Then for part D, we're going to find, so we find the probability that 0 is less than x less than or equal to 0.5, given that y is equal to 0.3 is equal to the differential from 0 to 0.5 of f sub x of x given 0.3 dx. Okay, so it's the marginal probability function of f of x given that y is 0.3. And so what's f sub x of x? Oh, okay, I wrote that before, right? Okay, so we found before that this guy is equal to f sub x of x given y is equal to the fraction 2x y plus, let me write it here, f sub x of x comma y, found earlier x given y, is equal to, this is for 0 less than y less than 1. What point y equals 0.3 falls in that range. This is equal to 2x plus 3/2 y divided by 1 plus 3/2 y. Okay? And so f sub x of x given y is equal to that for some y between, fixed y between 0 and 1. So here y is fixed. Okay? And so what is f sub x of x given y? It's that, where y is 0.3. And so you just plug in y equals 0.3 into that formula here. And so f sub x of x given 0.3 would be equal to 2x plus 3/2, where y is 0.3, divided by 1 plus 3/2 times y, which is 0.3. And so you plug that thing in here, and you get 2x plus plus 3/2 times 0.3 divided by 1 plus 3/2 times 0.3. That's 0.3 there, emphasize the period there, the dot there, and that's dx. So this guy is this guy. That's because this is equal to that. Okay, and we just substituted y. Where we saw y, we just substituted 0.3. Okay. And so now that is that, and then you find that definite integral, and you get that this is equal to 0.3276. That's the value of that definite integral. That's part D. Okay, now part E. Part is 0 is less than or equal to y, less than or equal to 0.4, given that x is equal to 0.2. And that's equal to definite integral 0 to 0.4 of f sub y of y given 0.2, dy. Okay, so the difference from 0 to 0.4 of that is this. Okay, so very similarly to part D, we found f sub y of y given x, and so you just plug in x equals 0.2 into that formula, and you get this. And then you integrate from 0 to 0.4 because those are the range values of y. X is 0.2, you're plugging in x equals 0.2 into there, and you're getting this. And so you find the definite integral, and you get 0.0914. Okay, and that's part E, and so that's the end of that example. Let's keep going. Okay, so now 7.2.6 is the multinomial distribution. Okay, 7.2.6 is the multinomial distribution. And so definition 7.6, let n and k be positive integers. Let p1 to p sub k be numbers such that the sum from I equals 1 to k of p sub I is equal to 1, and 0 is less than or equal to p sub I less than or equal to 1 for I values from 1 to k. The multinomial probability function f is defined by f of x1 comma x2 comma comma xn, which is equal to x of k, which is equal to n factorial over x1 factorial times x2 factorial times x of k factorial times p1 to the x1, p2 to the x2, p sub k to the x to the k. For integers, x1 to x sub k greater or equal to 0, such that sum from k I equals 1 to k and x sub I is equal to n. Okay, so definition 7.6. Let n k be positive integers and let p1 to pk be numbers such that the sum of those p sub i's is 1, and each p sub I is between 0 and 1 inclusive for I equals 1 to k. Okay, so the sum of the probabilities is 1, and each probability is between 0 and 1, including 0 and 1. Okay, and so the multinomial probability function of f, the multinomial probability function f is defined by that equation there. And it's for integers x1 to xk greater or equal to 0, and where such that the sum of the x of i's is n. Okay? Okay, and so you could also say that that probability, that's the probability that also equals that you can also say that that's equal to f of x1, that f is also equal to the probability that x1 is equal to little x1, x2 is equal to little x2, little xn is equal to little xn. Which is the probability of exactly x sub I occurrences of outcome a sub I for i's from 1 to k. Okay, so you would have x1 many occurrences of outcome A1, x2 occurrences of outcome A2, up to including x sub k occurrences of outcome A sub k, and it would equal to that. Okay, so that's the multinomial probability function f. So then, let's keep going. Okay, so 7.2.7 is the bivariate normal distribution. And so definition 7.7, let mu1, mu2, sigma 1, sigma 2, and p and rho be constants. It looks like a p. And be constants with sigma 1 positive, sigma 2 positive, and little p strictly between 0. Oh, it's p. Sorry. Little p strictly between 0 and 1. That's little p. The function f of x comma y is equal to e to the negative 1 over 2 times 1 minus p squared times in brackets x minus mu1 over sigma 1 squared minus 2p x minus mu1 over sigma 1 times y minus sigma 2 over y minus mu2 over sigma 2 plus y minus mu 2 over sigma 2 squared, all that in brackets, e to negative this fraction times that, all of that divided by, y, f is equal to that divided by 2 pi sigma 1 times sigma 2 square root of 1 minus p squared for negative infinity less than x less than infinity and negative infinity less than y less than infinity is the bivariate normal PDF, normal probability density function, abbreviated as PDF. Okay, so that's the definition of the bivariate normal probability density function. So that's another probability density function. F of x comma y is equal to e to the negative 1 over that times that divided by that. And that's for any xy value, any real numbers xy. Okay? Okay, good. Everything's good here. That's an E. Give me a chance to look at it and write things down. That's the bivariate normal probability density function. Okay. 7.3. 7.3 is on independent random variables. Okay, let me check this one. And so first we're going to, in 7.3.1, we're going to have definition 7.8. And so let x1, x2 to xn be random variables. Discrete or continuous. With probability functions f sub 1 of x1 dot 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 f sub n of xn respectively, and multivariate probability function MPF f of x1 comma x2 comma dot 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 comma xn. The n random variables are independent if f of x1 comma x2 comma dot 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 comma xn is equal to f sub 1 of x1 times f sub x2 times f sub n of xn. Good. For all values of x1 and xn, for all values of x1 to xn of capital X1 to capital Xn respectively, except at points of discontinuity. Okay, so definition 7.8. Let x1 to xn be random variables, discrete or continuous with probability functions f sub 1 of x1 to f sub n of xn respectively, and MPF f of x1, x2 to xn. The n random variables are independent if f is equal to the product of the f sub I of x sub i's. For all values of x1 to xn, little x1 to little xn of capital X1 to xn respectively, except at points of discontinuity. Okay, so what that definition is of n random variables are independent if you have this equation, basically, with conditions, right? Okay, so it looks just like independence in what we dealt with previously, right? You can now think of it as a product of these functions. The original MPF, you can think of it as a product of those probability functions. So that's definition 7.8. Okay. Example 7.17. X sub I is the value on the die, and X sub 2 is the number of heads from one coin flip. So X sub I is the value on the die, and X sub 2 is the number of heads from one, oh sorry, not X sub I, X sub 1. So X sub 1 is the value on the die, X sub 2 is the number of heads from one coin flip. And so I'm going to need to use the blue marker now. F sub 1 of x1 is the probability that x1 is equal to little x1, which is equal to 1/6 for x1 from 1 to 6. So if you roll a die, right, the values of x1 range from 1 to 6, the values on the die, and so the probability of any particular value in the die is 1/6. Okay, f sub 2 of x2 is the probability that the second random variable x2 is equal to some fixed number little x2. Well, that's just the number of heads from a coin flip, and so that probability is 1/2 for x2 equal to 0 or 1. So the probability of when you flip a coin that you get 0 heads is 1/2, and the probability when you flip a coin one time being heads is also 1/2, because heads is 1/2, tails is 1/2, right? So probably heads is 1/2, probably tails or not heads is also 1/2, or 0 heads. Okay, so we have f sub 1 of x1, f sub 2 of x2 here. We have f sub 1 of x1 is 1/6 for all those x values, and f sub 2 of x2 is 1/2 for all those values of x2. And so f of x1 comma x2 is equal to 1/12, we found before, for x1 ranging from 1 to 6 and x2 ranging from 0 to 1. Well, that implies, everything above there, that f of x1 comma x2 is equal to 1/12, which is equal to 1/6 times 1/2. And 1/6 is equal to f sub 1 of x1, and 1/2 is equal to f sub 2 of x2. Okay, and this is for all x1 and x2. Okay, so now we just showed that f of x1 comma x2 is equal to f sub 1 of x1 times f sub 1 times f sub 2 of x2. And so that implies, because that equals that x1 and x2 are independent by the definition of independent variables. So x1 and x2 are independent by definition. Okay, and so that's the conclusion. And so in example 7.17, we conclude that x1 and x2 are independent random variables, because we show that f of x1 comma x2 is equal to f sub 1 of x1 times f sub 2 of x2. Okay, so that's that example. Okay, so now we're almost done. Okay, now 7.3.2 is, so in that section, if you have x1 and x2 are independent, if A is the event that x1 equals to some fixed value little x1, and B is the event that x2 is equal to some fixed value little x2, all of that is equivalent to saying that the probability of A intersection B is equal to the probability of A times the probability of B. And so this is just pointing out in 7.3.2 how this new definition of independent variables is the same as the one we had before. And so, right, our new definition says that f of x1 comma x2, if that equals to f sub 1 of x1 times f sub 2 of x2, then x1 x2 are independent variables. You can just translate that into the probability of A intersection B equals probability of A times probability of B, where A is the event that capital X1 equals to little x1, and capital B equals x2. And capital event B is the event capital X2 is equal to little x2. So this is event A, and that's event B. Those are the events. Those would be the events in our normal definition of independent events A and B. Okay, so if we translated random variables to events, where the event was that our value would be some fixed x1, x2, we would see that this new definition of independence corresponds exactly with our old definition of independence. Okay? Because if event A is x1 equals little x1, and then event B is x2 equals little x2, the probability of A intersection B would be the probability that both x1 is equal to little x1 and that x2 is equal to little x2. Well, what that is it's the probability of f of x1 comma x2. But we know the probability of A intersection B is equal to the probability of A times the probability of B if those two events are independent. And so the probability of event A is the probability that x1 is equal to little x1, and the probability of event B is the probability that x2 is equal to little x2. And that probability is f sub 1 of x1, and that probability is f sub 2 of x2. And so I just showed here is that f of x1 comma x2 is equal to f sub 1 of x1 times f of 2x, so I showed that equation. Just assuming the original definition of independent events A and B. Alright, and so that part here, this equal sign here from independent events A and B, that allowed me to bridge this part and that part together. Because the probability of A times the probability of B is this, the probability of A intersection B is that, and if A and B are independent events, if these two are independent variables or equivalently these two are independent events, these two things are equal, which means those two things are equal. Okay, so that's that section. And so our final part of this last section. Okay, and so now 7.3.3 is independent random variables. Derived from independent experiments. Part A is E is the experiment. So if E is the experiment and capital S is the sample space, for E, so E is our experiment and S is the sample space for E. X, let's say X is the random variable on S. And let's say our experiment E is repeated n times under identical conditions. The random variables x1 to xn are independent if x sub I is equal to a random variable on the ith performance of E. From 1 less than equal to I less than equal to n. So if capital E is our experiment and capital S is our sample space for experiment E, and X is a random variable on S, and if our experiment E is repeated n times under identical conditions, the random variables x1 to xn are independent if x sub I is a random variable on the ith performance of E from 1 less than equal to I less than equal to n. So those are independent. That's what we're saying. Okay, so if you have an experiment and you repeat the experiment n times under identical conditions, the result of those n times repeated experiment are independent of each other, and so you can just say those n variables x1 to xn are independent variables, and so you don't have to do rigorous mathematics to prove that repeating an experiment n times results in n independent variables. You can just say that when you have an experiment and you repeat it under identical conditions n times, that your n variables x1 to xn, where x sub I is just the ith time you perform the same experiment under identical conditions, those n variables x1 to xn, you can just say they're independent without having to prove it. This is a fast way to show that n variables, random variables, are independent random variables when you just repeat an experiment n times under identical conditions. Okay? And part B, if E1 to En are separate and distinct experiments. So before we repeat the same experiment n times, now we have n separate and distinct experiments. And so the outcome of E sub I is no way dependent on the outcome for E sub j when I is not equal j. So the outcome of any of the E's are not dependent on any of the other outcomes for any of the other experiments. Okay? So we have n separate and distinct experiments, and for any of those n experiments, its outcome is in no way dependent on the outcomes of any of the other n minus 1 experiments. Okay, so that's what I wrote so far. So S1 to Sn are the sample spaces for E1 to En, respectively. If x1 to xn are random variables, defined on x1 to xn, or defined on s1 to sn, respectively, then they are independent random variables. Okay, so here in B, E1 to En are separate and distinct experiments. The outcome of E sub I is no way dependent on the outcome of E sub j when I does not equal j, right? The outcome of any of those experiments is not dependent on any of the outcomes of any of the other experiments. S1 to Sn are the sample spaces for E1 to En, respectively. If x1 to xn are random variables defined on S1 to Sn, respectively, then they are independent random variables. Okay, and so when you perform n separate and distinct experiments, you'll end up with n independent random variables. Okay, and so when you repeat an experiment in A, when you repeat an experiment n times under identical conditions, you end up with independent variables. And here, when you have n separate and distinct experiments, you'll also end up with n independent variables. And so those are two situations where you do not need to test whether or not your n variables are independent, right? So if those two things happen, you can automatically assume that the n variables you get x1 to xn, which are respectively the variables for your n experiments, you can assume that they're independent. You don't have to show that the equation holds, right? That f is equal to f sub 1 of x1 times f sub 2 of x2 times dot 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 times f sub n of xn. You don't have to show that in these two situations, okay? Right, and so if x1 and xn satisfy A or B, then they are independent, and they satisfy the definition of independence in definition 7.8. Okay, and so now we finished chapter 7 here. We are done with all the material for the course, and I will post some solutions to problems. And so I need you to study the lectures, I need you to do the homework, I need you to do practice problems, and to go over your answers in the video I post, and be ready for the test. Okay? Good luck. Bye.